time. All right, in order to properly annoy the internet, I should pray again. So, Heavenly Father, we thank you again for this day, and I ask that you'd help us to understand sets and naive set theory and all that in one time the file sort. In the name I pray, Lord Jesus. Amen. All right, so let's erase this business. What is a set? Is my question for you. Any answers while I'm erasing? It's a did you say what?
A group of objects.
A group of objects. I like that. You could also say it's a collection of elements. You know? These are all kinds of just dancing around the issue that it's a fundamental concept. But various, the careful study of sets really came about in the 19th century. And it's probably wise for us to spend a couple minutes just talking about the history of that before I get too far into the examples and definitions today. So I would say that set theory was first really carefully studied in the 19th century. And, especially Cantor, he developed ideas about infinity, and he, proved what we call Cantor's theorem, which we'll get to much later in this course. But ultimately, it led to this, so this process of being more rigorous in mathematics led us to this sort of cliff where all of a sudden we were like, wait a minute, this doesn't make sense. And it ultimately culminated in what's called Russell's paradox, which is this. A barber in a certain town has stated he will cut the hair of all those persons and only those persons who do not cut their own hair. Does the barber cut his own hair? So if you can understand this sentence, it's really annoying. It's pretty much, it's a story to really beg the same question, which is begged by Cantor, if he allows there to be a set of all sets. Is the set of all sets a set? See this, anyway, I don't want to get into it, but if you dwell on these matters, there are contradictions and problems, all right? So there's something troublesome about having a this kind of ultimately self-referential set. And this led to the study of axiomatic set theory. So Zermelo Hilbert was one person. He had a set of axioms to describe geometry. There was Zermelo. He also had a set of axioms to describe set theory. Ultimately, there's this Zermelo. I can't say the word right. Some days I can say this name, Zermelo Fraenkel set theory, which sets out a system of axioms to describe set theory very carefully. But this system of axioms is so careful that it would be totally distracting to us. So it turns out that we can pretty much study set theory as Cantor was doing, as long as we're careful not to ask certain questions. Like, what about the set of all sets? So we just say, hands off. We avoid Russell's paradox. And this is pretty much the procedure that mathematicians have been operating under for the better part of a century now. But there is a careful system of axioms that forbids that Russell paradox, all right? But it comes at the cost of great, in my opinion, it comes at the cost of enough, what's the word? It muddies the waters so much at this point in the course that it's really unhelpful. So as much as I'd love to be axiomatic and as careful as possible in here with regard to set theory, I'm just not going to because it wouldn't be helpful. So we're instead going to study naive set theory. And naive set theory rests on two basic principles, which is the axiom of comprehension, that any collection of objects which you can describe and list can be collectively viewed as a set, which is more or less what you guys just told me, right? And also the axiom of extensionality, which is that if two sets have the same elements, then they are the same set. In other words, nothing but the elements contained in the set characterize the set. All right? So that's where we're going to go. So mostly, to start with here, I need to set some definitions for you. This is mostly notation, but here's our definition. We say a set is a collection of elements, all right, if if we write this, if x is an element of S, then we say, this is, I'm defining this notation right now. I mean, we've been using it all semester, but then we say x is an element of S. So you've got two choices in this course. You can either talk about set theory first and do some violence to the program of logic, or you can do logic first and do some violence to the program of set theory. So I chose the latter path. Dr. Sperano in the past has done set theory first and logic second. You could go either way. I think that truth tables are really easy to understand and a good place for us to start the course. That's why I did that. All right. So anyway, X is an element of S, and the set, empty set, is the set with no elements. All right, this is called the empty set. And I do say the empty set. I have a proof that we'll probably go over a different day, maybe next class, that the empty set is unique. There's just one empty set. All right. What else can I tell you? The set A1, A2, dot, 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 dot. This is roster notation. Like a sports team, right? Where you list the people in the roster, you know. So that has, I should say, in roster notation, comma, it has elements what? A1, A2, and so forth. We can also use set builder notation. What's set builder notation? We often use this notation. Here's how that goes. X in U such that P of X. That's supposed to be a curly bracket. These are all supposed to be curly brackets. Sometimes I succeed at making a curly bracket, sometimes not, but I try. So let me unwrap that notation. So here, this means, in words, what we're saying here is, this is the set of elements taken from U, which satisfy proposition P of X. All right. So in other words, the set builder notation, the vertical line can be read such that. All right. Whatever comes to the left of the vertical line, that's the elements in the set. Whatever comes to the right of the vertical line, that's the condition which perhaps binds the elements in that set. All right. Now, there's two popular notations. I almost always use vertical bar. Some other books or other authors or other professors, you might find them using a colon here. I do not use that notation. You won't see me use that notation. But you should know that's another popular notation. I would ask that you use the vertical bar, please. All right, for my class. But that is my choice. So. See if I have a good example for us here. Some sort of basic things. Ordering doesn't matter. So like A, B, C is equal to B, A, C is equal to C, B, A, etc. All right. If we want ordering to matter, then we talk about ordered sets, but that's a different matter, all right? There are places you want to talk about an ordered set, for example, in linear algebra. If you're talking about a basis, you're talking about an ordered set, so the order matters, but in just plain old set theory, the order doesn't matter. The other thing that's kind of funny is repeated elements. Repeated elements not allowed, I guess you could say, or at least absorbed. What I mean to say is, if I have 1, 2, 2, in set theory, that's just the set 1, 2. Kind of nervous to even write this in here. I feel it's going to get me into trouble. But if you want to distinguish between these two things, whatever they are, you'd need the concept of a multiset. A multiset is like a set, but it allows for repeated elements. Right? Some people feel the need to work with multisets. I don't find that's a useful concept for me. But there are people who do. For example, the linear algebra book written by, I think, James Hendricks. I may remember, James Heffron. All right, I shut up. Moving on here. Check this out, example. If we look at the empty set, we could also look at x in the reals, such that x squared is equal to minus 1. How many real numbers satisfy x squared equals to minus 1? Right? The same real number, like this, none, right? How about the natural numbers, such that n is less than 0? Right? How about, what else I got here? Oh, let P be any proposition. P be any proposition, not P and P, right? So all of these conditions are not satisfied. There's no element that satisfies the condition, right? The condition in these set builder sets, they're all false categorically. So these are all the empty set. Another notation for the empty set, of course, is just brackets like that. Now, before I get off the notation kick here, I should mention that there is another flexibility the set builder notation allows. So, what example am I on? I've lost track. Let's see. This was example. I guess this is example 1 in this video, isn't it? Should I keep numbering from the earlier ones? I'm going to start the numbering over again. This is example 1. So example 2. I could do this. I could look at S equal to k squared, such that k, oh my bad, good grief, n in the integers, such that n is equal to k squared for some k in the integers. Do you guys have a question, or did I write something funny? I heard some talking. Was it nothing? It was nothing. Okay. So we could study this set, right? And that's a reasonable set, right? We're talking about, this is squares basically, right? Like explicitly, this is 1, 4, 9, 16, 25, 36, 49, et cetera, right? But there's another way we could write this, and I do find this to be a useful way sometimes. We could also characterize this as like k squared, such that k is an element of z, right? Yeah. And if you think about it for a second, you realize I could also just characterize this as like k squared such that k is an element of the natural numbers union with 0. But that begs the question, what on earth is this union I'm talking about? I've been using it all semester, but maybe we should define it, you know? Maybe. Maybe we should define that, right? So my point is you can kind of build aspects of the condition into the thing you put to the left. And that is at times very convenient as a way to characterize a set. All right. So let me get some definitions off my chest here. Because we need to learn these definitions. And once we learn the definitions, there's all kinds of fun things to prove here for set theory, right? So, question? No? Okay. First of all, subset. So definition, let A and B be sets. All right. If X, an element of A, implies X is an element of B for any X in A, then A is a subset of B. I guess I probably should say at this point, then we write A is a subset of B, and this is read. A is a subset of B. All right. That is not an angly thing. That's a curvy thing. If we write the angle thing that's less than or equal to, that's a different thing. All right. So subset. A is a subset of B. In this context, we also say B is a superset. A superset of A, and B contains A. So this is read B contains A. Furthermore, if A is not equal to B, then if A is not equal to B and A is a subset of B, then A is a what? Quote unquote proper subset of B. If A is not equal to the empty set and A is a subset of B, then A is a non-empty subset. Of course, this is just kind of a specialization. I'm not sure I really need to honestly, folks, I'm not really sure I need a standalone definition here. Like, we probably should just define empty set, and a non-empty set is any set which is not the empty set, right? That's a broader definition than the particular context I'm using here. So, all right, so really the top line is the most important one and the most commonly used one, subset, right? Next up, what do we mean by so like here's a proposition that's stupidly easy to prove. A, any set, then I should say let A be any set, A is a subset of A, and the empty set is a subset of A. How's the proof of that go? Let X be an element of A, right? Let X be an element of A. Then, this is very silly. X is an element of A. Thus, A is a subset of A. On the other hand, since there does not exist X an element of the empty set, it is vacuously true that X an element of the empty set implies X is an element of A, right? Oh, what have I done?
What does vastiously mean?
Vacuously.
What does it mean?
What does it mean?
I've just never heard the word before. I'm sorry.
Well, I mean, it means that it's automatically true because there's nothing, I'm explaining what it means here, I guess. So this is automatically, we use this term vacuously true when we're establishing some claim where there's nothing to check the claim against, basically. So like here, X an element of the empty set. Is there any X which is the element? No, there's no X that's the element. So it's vacuously, this proposition is vacuously true because X an element of the empty set is automatically false. And we know that the conditional is true if the antecedent is false, right? Like you can put whatever you want over here, right? X is an element of the empty set implies X is the president of the United States. Implies, you pick whatever kind of crazy thing you want to put over here, But anyway, we'll just stick with X as an element of A because that proves that the empty set is a subset of A. All right, so you got that. Another proposition, and we use this one a lot. Let A and B be sets. That was supposed to be a B sets. Then A equals to B if and only if A is a subset of B and B is a subset of A. We'll refer to this by so-called double containment. So there should be a bunch of proofs you see as you go on in the math major where we make a double containment proof. To prove two sets are equal, we show that one's a subset of the other and the other's a subset of the one. All right? Now our definition of equality of sets, one of our axioms at the start was that two sets have the same elements, they're the same set, right? So that's really all we have to work with here, is to prove that if, our definition for this is what? So this means A and B have same elements, right? That's the definition of them being equal by our axiom of quote-unquote extensionality. All right. So then if we assume this, right? Then what? Check it out. If X is an element of A, that implies X is an element of B, right? And also if X is an element of B, that implies X is an element of A, right? Thus what? This would say A is a subset of B, and this would say B is a subset of A. So that's the forward implication here. If they have the same elements, if you pick X in the one set, it's automatically in the other, and vice versa, which is to say A is a subset of B and B is a subset of A. Conversely, if A is a subset of B and B is a subset of A, note if X is an element of A, then since A is a subset of B, we find X is an element of B by the definition of subset, right? Likewise, X an element of B implies X is an element of A, since B is a subset of A. So, in summary, A and B have the same elements. Therefore, A is equal to B. So this is fundamental. We can check for equality of two sets by showing this double containment. It doesn't seem like I'm really saying much of anything, but when you get to actual proofs a little bit later, like next class we'll see that this is actually a thing. I know it almost seems too simple. It almost seems like something so simple that you can't even prove it in some regard. Now, the biggest shortcoming of my notes at the moment in the set theory regard, I think, is probably the fact that I don't have any pictures for union or intersection or complement or set difference. So I'll be trying to add those pictures in class, all right? Those pictures are, of course, the famed Venn diagrams, among other things. So let's get to that. Where was I? Make sure I'm not skipping something. Sometimes I get ahead of myself. Well, anyway, I'll let you read Proposition 3.111, which is that the empty set is unique. All right. So I wanted to make sure I defined union intersection for you guys today. So definition: if A and B, I'll give you a twofer, our sets. Actually a threefer, all right? So A union B is X such that X is an element of A or X is an element of B. On the other hand, A intersect B is equal to X such that X is an element of A and X is an element of B. This is intersection. So, defines union of A and B, defines intersection of A and B, and by the way, as a point of order, like if you're studying for like a future quiz in terms of stating a definition, I would tend towards looking at the notes, the definition there, as opposed to whatever I write on the board, because sometimes in the heat of battle in class I might miss something. I would say it's safer to look at the notes probably, just as a point of best practice. I try to recreate proper definitions on the board, but I don't always succeed. I try though. If you see something, say something. This is set difference, A minus B. Now other people have another notation, but I like the minus notation because, I just do. So what we're talking about here is X in A such that what? In contrast, B minus A would be what? x in B such that what?
X in A such that X is not in B.
Very good. X not an element of B. And the next one is x not an element of A, right? So the last two are sometimes called set difference. They're sometimes called the relative complement. Like, so these are set differences. All right. So like I said, I wanted to add some pictures. So let's do that. I think I've got about enough time for that, but maybe not much more. So typical picture, you draw a box like so. Do. And then, so the box is supposed to be the universe, which we'll talk more about next time. The universe is the context of all possible numbers in which your sets are, being formed. Oftentimes for us, the universe is like the set of real numbers, or natural numbers, or integers. But in some sense, the universe was the set of all functions on R for that one example earlier today. Context matters, though, and that's essentially what the universe is. But here, my red circle and my blue circle are going to illustrate, respectively, the set A and the set B. These are Venn diagrams. So I'm going to make the red circle B. I'm going to make the blue circle A. And then I'm going to put in green each of these set operations I've defined up here. So A union B is just everything. X is in A or B, so it's like all of this, right? This is A union B. The intersection, on the other hand, like it sounds, it's just the points that are in both, right? A intersect B is those points. How about A minus B, where every point that's in A but it's not in B, right? So that's like, kind of like, not exactly a Pac-Man, but it's this piece over here, right? That's A minus B. On the other hand, over here, this is what?
B minus A.
Yeah, B minus A. We got all these pictures up here. Can you guys use these pictures to make a quick conjecture here before one last conjecture before we end class? What would be a conjecture we could make here? A mathematically educated guess. How about this? If I said A minus B unioned with B minus A, what do you think that would be equal to? If I take these, yeah? Do you guys agree with that? What do you think? I agree. It's the whole of the union removed the piece which is missing when I union these two differences, right? That's a good conjecture. These pictures don't prove it, but they say we're probably on the hunt, right? To prove this, we could give a double containment proof. We'd pick, X is in the set on the left-hand side and show that X is necessarily in the right-hand side and vice versa. If we can show that each one of these is a subset of the other, then we've proved that they're equal. Yeah? Anyway, we'll do that kind of thing next class. So, thanks, guys.